Okay, what I want to talk about right now is simpler. I'm going to talk about replica server placement and content replication and placement. And then a bit about content distribution. And tomorrow, at least I hope to come to that point. Tomorrow I will talk about the implementation of these continuous consistency models. And that's a bit tricky, I'm afraid. Okay. Now, interestingly, a couple of years ago, we did a big survey on web hosting services, or actually replication in web hosting services. And we read about 120 papers. And I can assure you that's a lot. And everybody was talking about content distribution and whatnot, but very, very few researchers were making a distinction between the problem of where to place replica servers, and once you have those in place, where to distribute the content to. So just imagine that you want to start a web hosting service, an internet-based web hosting service, meaning internet-based all around the whole world. You will have to place servers across the internet, okay? And placing servers means that you just hire rent space at data centers and whatnot. And the first decision that you have to take is where? Which data centers do I go to actually rent stuff, if you can actually make that decision. And that is basically your replica placement problem. Once you have the servers in place, you can start deciding on where to ship content to. This is very much along the same lines as the globule research that I talked about, what was it, the first or the second class, where we had this self-replicating system that just simply took a look at where requests came from and then said, okay, by means of a what-if analysis, aha, that web page should be over there, that web page should be over there. But if you don't have a server over there, there's no decision to take. Okay, so the first thing I want to do is concentrate a bit on replica placement. Where is the best place to place your servers? So basically figure out what the best K places are out of n possible locations. Those with a somewhat mathematical background will instantly say, ha, this is a tough problem. First thing that you could do is you could try to select the best location out of n minus k for which the average distance to the clients is minimal. So we're assuming that we do know where the clients come from. Okay? And then choose the next best server, and then the next best server, etc. The first chosen location minimizes the average distance to all clients. It turns out that this is computationally expensive. And when I talk about computationally expensive, I mean really computationally expensive. That means if you want to do the full computation, you may need a big supercomputer to actually do all the computations, and then you'll die before it's finished. So you use a heuristic to actually find out what the best could be. Okay, that's one thing. A more practical one could be select the K largest autonomous system and place a server at the best connected host. Now you have to figure out, so an autonomous system is ISP. Okay? The kth largest ISP, and the idea is, of course, that you have many clients to that ISP, and then choose the best server in that ISP. Turns out to also be computationally expensive. Basically, the first two problems are very much connected to each other. So it's in both cases we're talking about a facility location problem, solving a facility location problem. Now, with finding the best servers, it's a comparable problem. You have clients all over the place, and basically what you're looking for is to try to find the best place for a server. But the problem is that as soon as you've placed a server over here, you will have a second choice for the server over here. So basically you're ruling out any other optimal solution because you just reduced your space, right? And that's the problem. You never know for sure by placing a server over here whether that indeed will lead to the overall best solution. This is the same thing with the bin packing problem. You place something without knowing what other groceries are going to come along your way, and you just hope for the best that you just packed everything in an optimal way. That will lead to an optimal placement in the whole cart. Okay? Don't worry, this is not the way that I do groceries all the time, but I just pack things and then... Now, and what makes it computationally expensive over here is that I take the distance from clients to my servers into account. So that means you have to, in principle, do a lot of computations, basically figuring out all the distances from clients to servers to see if you have the optimal solution. In theory, you would have to do this. You have so many servers, you can throw in so many servers into the system, and then you can do a computation, and then you can probably rearrange things, and you may get a better configuration. That's fine, but if you do it like that, that's just endless. It's basically a trial and error approach. Thousands. Oh, we're talking about a big problem here. Now you can simplify, just a minute, you can simplify matters by the system I described last time, position nodes in a d-dimensional space. And you know by now that d is 6. Okay? The trick here is that if you can place all the servers as well as the clients in this d-dimensional space, you could suddenly do computations. You can simply say, okay, I can optimize. I have so many clients over there. I can simply compute what the best places would be to minimize the total distance to clients. And that's almost a straightforward computation. It certainly is linear. Linear in the sense that I think it's quadratic or something like that. It's quadratic in the number of servers. So that's much, much cheaper because the other ones are basically exponential. That's a very good question. Do we have to find the optimal solution or a good solution? No, you will only have to find a good solution. So what it turns out is that in both of these cases, you will resort to heuristics, and for those heuristics, you can prove that they are generally good solutions. In many cases, and off the top of my head also for these, the problem is how good are you? Finding out how good you are. So that means that you need to have an estimate of how good you could get. So that means what could the optimal be? And that's often sometimes something of a nasty problem. Certainly if you are talking about placing thousands of servers. Thousands, by the way, is not an exaggeration. Akamai, one of the big web hosting services, has, to the best of my knowledge, over 20,000 servers, probably something like 30,000. If you want to really place if you want to have the best K servers, no, the best K places out of n possible locations, that problem is an NP hard problem. That makes it computationally expensive. The solution you're providing is one that could work, but you never know for sure. Oh, okay. So, again, I'm not saying that you cannot find good solutions. What I'm saying is you take a look at the general problem, it is a computationally expensive solution. Even if you would apply genetic algorithms, which is just another way of finding this, you will, I would agree actually, you use genetic algorithms to most likely find a good solution, a truly good solution, faster than any, kind of traditional heuristic that you would apply. I agree. So I'm not saying that it cannot be done. I'm just trying to make clear that this is a difficult problem in general to solve. Okay? And in practice, yes, what would happen in practice? If you were Akamai, you would probably just go for the cheapest. So in that sense, this is more of a theoretical problem, because in many cases, the initial distance doesn't really make a difference. What you will do in practice is that as soon as you see a lot of clients, for example, downloading a lot of video content, or actually I should say downloading large files that are hardly ever modified, you just rent another server over there and you place it over there. That's the engineering approach. Okay? So much for replica placement. Now get into a mode that I have my replica servers all over the place. Now I need to decide on where to place my content. And for that, you can think along these lines. You have permanent replicas, often only one. We call it the origin server. You have server-initiated replicas. This is stuff that one of the permanent replicas, it notices what's going on and says, I want the content over there. And it places content over there, okay? And then you can have client-initiated replicas, and we call them caches. Installed at the client. Now, the interesting thing about a client, and then you get kind of this picture. You have your permanent replicas. This is the abstract view. Your permanent replicas, read one, your origin server. Around that, you have a bunch of server-initiated replicas. This is where let's say your origin server takes the initiative to place content at other servers. And then around that, you actually have clients. And the interesting thing about the clients is they can have caches. And you do not have control over what clients place in their caches. Despite your hints like, don't cache this. A client can still do that, okay? You have no control over that. So when you talk about a distributed system, you can control this part up until the server-initiated replicas. The client-initiated replicas are out of your control, okay? That's the main difference. Now let's take a look at server-initiated replicas. How does this work in practice? This is a largely simplified scheme of a system that was built years ago by colleagues at that time working at, I think it was AT&T actually. Misha Rabinovich actually is his name. Together with Fred Douglas, I think Fred and Misha actually built the system. But this is a good illustration of how these things can actually happen. Now, what's the model here? You have replicas. No, sorry. You have replica servers, one over here and one over here. And this guy holds a copy of this file F. And the whole idea is that you place this F as close as possible or reasonable to where it needs to be accessed. And again, don't think of small files, think of large files. I gave this example last time that if you have, let's say, a video file and it's placed really close to you, then TCP will react accordingly and will make sure that you can actually access this file. Even if maybe it's the TCP control path or whatever, having stuff close by will actually improve our latency and bandwidth. And maybe the video in combination with TCP is not a good example, but you get the picture. And the reason why I'm mentioning this, that if you have your file at the other side of the world, well, if it's a very small file, it doesn't really matter because, probably latency is not your biggest problem. But if it's a big file, then bandwidth is a problem, and the internet reacts dynamically to providing you bandwidth if things are far away. If they're close by, you get automatically more bandwidth. Okay, so that's the thing to keep in mind. Now, what this system does is the following. You keep track of access counts per file. You aggregate it by considering the server closest to requesting clients. Woo! What does this mean? If you have this client over here that wants access to that file, the system will, I'll first say, pretend that that request actually passed through P and then went to Q. Okay, how would you implement this? You simply use a proxy. Okay? So the model that you can think of this is C1 actually enters the distributed system through a proxy. The proxy has knowledge of where servers are and can do the accounting. And can even say, well, I'll just forward it through P and let P do the accounting. Because it happens to know how what this thing looks like. Okay, the number of accesses can drop below a certain threshold D, you throw away the file. Well, almost. If the number of accesses exceeds a certain threshold R, you replicate the file. And if it's somewhere between D and R, you migrate the file. Oh yes, there's a very big problem. If I would follow these bullets, I would have a problem. Why would I want to make the distinction between replication and migration? More space. Hey, storage comes for free nowadays. The more replicas you have, the more expensive the update operations. Not because of traffic. Let's say I have 10,000 replicas of a file, and I update it. What's going to hurt? Concurrent. Who said that? In what sense concurrency issues?
Multiple writes.
So what would be a pessimistic scheme to avoid concurrency issues? Now you see the answer. Simply do not allow any update until the previous update has finished. That's sequential consistency, right? That hurts. Now, if you have only 5 copies, hey, it may be doable. And you could have, watch this, an interesting trade-off between read performance and write performance. So it's very simple. If you have a file that is hardly ever updated, pick a high replication degree. Okay? So you would replicate more than in the case of a file that has a relatively high write ratio or write to read ratio. You would say, whoa, I don't mind replicating, but I'm not going to replicate 10,000 times because that will lead to a performance degradation because of the synchronization I would have to impose because of sequential consistency. You see how things gradually fit together? It's not every... they're separate pages, but they actually have, they are related to each other. Let me put it that way. But there's another problem that's on this slide that I'm just neglecting. Your file can disappear. You wanted to say that. You both said it. The file can disappear. Right? Below a threshold D, drop the file. Yeah, sure. That page is never read. Bzz, oink. So how do you, what do you need to do? Basically, you just make sure that there's at least always one on a well-known location. Yes. And then make the origin server responsible for keeping files no matter what replication strategy you're applying. I'm not quite sure whether I made this so explicit, but yes, it was certainly implied. Absolutely. What? You have to realize, can P become a bottleneck? Well, there are many, many Ps.
But you said there is only one source, the permanent.
There's one permanent source. That's the origin server. And every file could be associated to a different origin server. That's not the problem. There is, first of all, it's a migration between replica servers.
Yeah,
And in principle, no, this is a decentralized control. So this guy over here can say, okay, listen, I'm not having enough accesses. Basically, the number of accesses that I'm seeing over here drops between this D and D and R. I'll just migrate it to P. Okay? They actually implemented this stuff, actually. Okay. Let's take a look at content distribution. And for the next stuff, I will mainly be getting back into client-server mode. So keep that in mind. Now, again, client-server combination. And the client could be a cache, for example. Could be another replica server. Just talking on a one-to-one basis between a replica server over here and a replica server over here. Okay? Now, what do you do with updates? Well, what you can do is you can propagate only the notifications or invalidations. So I'm assuming that a server is over here, you have a server-initiated replica over there, and this server, being responsible for that data, can say to that server, what you have over there is no longer valid. Okay, that could be a decision you could make. That's a choice you can have. Okay, and you often use this specifically for caches. You can transfer data from one copy to another. This generally happens in distributed databases. This is called passive replication. What this means is that if I, as a replica server, see an update, I move the entire updated data to my replica server. Right? So if a table is updated, I move the entire table and I overwrite the value that you see at the replica server. What you could also do is propagate the operation. This is called active replication. It means that I get an update operation executed on my table, and I propagate the update operation to my replica server and say, will you please execute this operation as well? And if I do this in the same order everywhere, the result will be that all my replicas will be exactly the same. Okay? These are the things I can do. And of course, by now you should know, we're talking about distributed systems. No, there is no single best solution. Good. Now, let's take a look at the content distribution in the client-server system and pushing updates and pulling updates. So pushing updates is what you do with a server-initiated approach. And an update could be a notification, the operation, or the complete data. Okay? Pulling updates is like, let's say I got a notification it's invalid, and say, okay, let me go over to the server and fetch my update. Or I could actually also from time to time just probe my main server, say, do you have anything new for me? If you take a look at the state that needs to be maintained at the server, the main server I should say, and the other one is the replica server or the cache or whatever, you can then see the following distinction. So first, the state at the server in a push-based approach is, well, you have to list where your clients are. You have to maintain where your stuff is. Okay? In the pull-based stuff, hey, who cares? You don't need to know them, they will come to you. Okay? If you take a look at the messages to be exchanged, then in the push-based approach, you have to propagate updates and possibly also a fetch update. The fetch update comes from the fact that you only push an invalidation, but then you should expect the update operation to come back to you from that replica server for fetching the actual content. In the pull-based approach, the only thing you can do is pull, okay? And then once in a while you actually, fetch the update. If you take a look at the response time, you again have another trade-off. In the push-based, it's there, okay? If you push the entire update, it will be over there. So that means that when a client goes to this replica server, it will always find the up-to-date information. The worst that can happen is that you propagate invalidations, in which case that server, knowing that it now has invalid data, has to go to the main server, fetch the content, and then the client is happy. Okay? Now we get to one of my favorite slides. You can dynamically switch between pushing and pulling. So the first thing you have to realize is that if you take a look at the pull-based approach, it scales like hell. The server basically doesn't have to maintain state. It will have to send updates on request, and it may not always be the best when it comes to providing immediate updates at the caches, but maybe that's good enough. Now, if you switch between pushing and pulling, you may get into a situation that the server, the main server, will say, listen, replica server, I will promise you for a while that I will keep you completely up to date. The big benefit of that could be that your clients always have up-to-date information. And there may also be other benefits, like the ones that I discussed when I was discussing Globule. It may also be cheaper for you. To give you a good example, if there are hardly any updates, I'll get to that in just a minute, if there are hardly any updates, you can keep a promise to this other replica server. Don't come to me. I will hand out the update when it's there. And that will save you traffic. Okay. So here's where the leases comes in. You don't want to promise this forever because, there could be a gazillion clients out there, if they're caches. The interesting thing is that if you maintain a time for the leases, you don't have to actually promise too many servers stuff. There was a, what was it? There was a research done on, I think I should call it Web 1.0, 1998, where you just had caches and servers. And what these people did was to see how many servers, no, how many caches an origin server needed to remember when it had leases that lasted, off the top of my head, 2 days. Okay? And this basically means that a server would keep information on where its caches were placed that had its content. Do you have any idea of how many caches a server needed to remember? What do you think? This was in 1998. But just to see gut feeling. What do you think? Hundreds, thousands, millions, tens of thousands? Whoa. So basically I'm suggesting that, let's say after 24 hours, the server says, sure, go away. I'm not going to, if you now want data from me, I just removed you from my list. You come to me, and then basically switching from a pushing system to a pulling system. Anybody, any gut feeling? Few hundred. Who would say hundreds of thousands? Nobody. Hmm?
What kind of caches? Caches in the distributed system or all clients?
Web caches. So let's say proxy caches. There are, I don't know, millions of proxy caches out there.
But not on the clients itself, but like proxy cache from home.
Yeah, I think this experiment was done on proxy caches, not web browser caches. So not millions. 100,000? Distributed systems is a lot about numbers. So what do you think? Your suggestion is actually probably everyone has their top so many. Turns out that in this specific experiment it was about 5,000. Is 5,000 a lot? No. No. The only thing you have to do is maintain a list of 5,000 caches. And when you do have an update, you send them a mail. Say, hey, a message, I should say. Got an update. A mail, yeah. You can actually do that, but there's. So I'm saying this, and I see your point. It depends on what server you are, what type of service you're providing. But it's the gut feeling like, it's not that many, despite the fact that there, at that time, were already millions of proxy caches out. And their average was 5,000. And in 1998, just to give you a clue, this is about the same time that we did the research that I showed you during the first or the second class. So it turns out that we had, at that moment in time, requests from approximately 2,000 to 4,000 different autonomous systems. And the clue was that 70% of all the requests came only from, I'll exaggerate a bit, a handful of autonomous systems. So the clue is that there is only a relatively small group, and I'm not talking for Google, a relatively small group of autonomous systems where you can expect requests from. If you would then even count servers, it always turns out that it's a relatively small group compared to all the available servers. If you then couple that to a time at which you would send updates and say, after that, I'm gone, that group can remain relatively small. But you're right, it all depends. I can easily come up with exceptions. But it's the general feeling about this. It's relatively small compared to what's all out there. Exceptions to the rule. And then you would see very similar numbers, at least the ratios. Now, what we tend to do as systems people is build our systems for the worst case. We should not do that. We should build our systems for the average case, and the average case is generally very good. Then there will be many exceptions, And then we should pay attention to those exceptions. How important are they? Okay, but I want to get to my fun slide, okay? And the fun slide is, okay, a lease. Now, what can you do with leases? First of all, a very common one is you use age-based leases. So what the main server does, it takes a look at, and this is the model. I'm going to replicate a file to that replica server over there, and now I need to decide on what the lease would be for promising that server that I will inform that server about updates on that file. And an age-based lease says, well, if that file hasn't been changed for a very, very long time, I'm going to make the assumption that it's not going to be changed in the near future. So what I'll do is I'll give this a really long-lasting lease. And of course there's an exception, because you could say, well, if it hasn't been changed for a very long time, I would bet on that it will be changed very soon. Okay? But you're not making that bet. You say, hey, my history is a good indicator for what happened in the future. It's not going to change. That's an age-based lease. This is a very common approach. This is what you do in web caches. You know, if it hasn't been changed, well, you know, keep it in your cache for a long time. It's a kind of a boring one. I like this one. The renewal frequency-based lease. The more often a client requests a specific object, file, the longer the expiration time for that client. If a client continues says, do you have an update, do you have an update, do you have an update, you get bored with this client, you say, go home. As I say every year, it's the model, don't call us, we'll call you. And it's very efficient because you're saying, don't come to me, stay away, I will tell you when there's an update, because you're just bugging me, okay? And your bugging me is more expensive than me sending you an update when the update is actually there. That's the model, okay? Then there's a tricky one. It's the state-based lease. I by now should say this is actually, this is what people do under stress. If people are under stress, they say, go away. But that's not going to solve your problem, okay? The state-based lease is said the more loaded the server is, the shorter the lease time. And, hold it. Why are we all doing this? Well, in the first two cases, you're really trying to get people off the back of the server. You're trying to optimally configure the server by saying, I want to do the least possible I can do without being bugged or whatnot, so that, you know, I can keep a, let's call it a strong consistency. And this very much holds for the first two, but not for the last one. If you're stressed, maybe it will be good to hand out these leases, because then you wouldn't have all these buggy clients coming to you. Yes? So let me be clear on this. The state-based lease is exactly what you would do when you're stressed, but it may not be the optimal strategy. A better strategy could be like, I'm so stressed. Listen, I will tell you when there's update. Don't knock on my door anymore. And that will, you know, put you in a relaxed mode. Exactly. So they do this under the assumption that it will offload the server, but that assumption is not correct. It is only correct if the client comes with more requests than there are updates. And that means that for these first two, those are actually good strategies for offloading the server. But the third bullet, it really depends. It's certainly not a guaranteed strategy. The content can remain in the cache long. Hold it. I have to correct myself. No, I have to correct myself. In the age-based lease, what you will do is that you will let the server promise to send updates to a cache, expecting that the file will not be changed anyway. So if I have a file that hasn't been changed for ages, it's an extremely cheap promise to say, hey, I'll keep you updated. Because your expectation is that you don't have to send any updates. Right? And if you happen to do this, okay, here's an update. That's the model.
If you're under
And if you're under a lot of stress, what I'm saying is that in these two cases, the lease makes sense and will help to further offload a server. And offloading means you won't get requests in, you will promise to send the updates, which is cheaper because you're expecting more requests from clients to see if that there are updates than that you need to send updates. That works in both cases. So you're offloading the server. And it's not valid for the third one. Because in the third one, it really depends. Okay, watch this. Okay, this is interesting. So let's say we have a stressed server. Okay? And let's define that the server is stressed because it's getting a lot of requests from clients. So the question is, how can it make sure that it gets less requests from clients? What strategy should it apply? I have three strategies here. Which strategy should it apply? The renewal frequency-based strategy. And what will happen is exactly what you guys just mentioned. The clients will come less to the server under the assumption that there are more requests from clients than updates. Okay? Now let's drop that last assumption. There are actually lots of updates on a file. What should the server do? Yeah, in this case, it can so different ones. If you get a lot of updates, your conclusion would be that at the moment that you suspect that you have to send more updates than handle requests from clients, well, there are different things that you could do, but you could say, well, then I should have promises. Don't forget that if you always have a lot of updates, yes, let me put it this way. If you have really a lot of updates, would you actually use long-lasting leases? If you have a lot of updates on your files, you know what I would do? Shut up. I wouldn't tell anybody. Right? As long as I haven't made any promises, I'm safe. Because I don't know anybody who could be possibly interested in all those updates. And if somebody happens to be interested in that specific file, I may have been able to process locally 10 of those updates. Hey, he gets 9 for free. I didn't have to do anything. So this is how you should balance these things. And from all the leasing strategies, the state-based lease strategy may or may not help you. Okay? And the others will help you. You have to do some accounting. Okay?